Hey everybody, let's dive right into the proof of the theorem that I stated at the end of last video. So to remind you, here's what that theorem said. It said, let capital G be a cyclic group, which is generated by an element lowercase g. Then the order of that element lowercase g is the same as the number of elements in the group capital G. And let me even add on one more phrase to this, which is that the two sides of this equation are equal to one another, even if both sides of the equation are equal to infinity. So what I mean by that is that it could be the case that the element lowercase g has order infinity, and it also could be the case that the group capital G has infinitely many elements. But if this happens, then they'll both be infinite. So both sides of this equation will be infinity, and so, well, it'll still be a true equation in that sense. All right, so let's start proving this theorem, and the first step is to write out what the elements in a cyclic group capital G really are. Namely, by definition, when we say that the group capital G is equal to the subgroup generated by the element lowercase g, that means that its elements are the identity and lowercase g as well as all of its powers, and G inverse as well as all of its powers. But it might be the case that when I write out this really long list, some of the things I've written are the same. Like, I don't know, maybe G squared is the same as G to the 7th, for instance, or G inverse is the same as G to the 4th. To think about which of these might be the same as which other ones, we'll break the proof into two cases. First, if order of G is infinity, and then second, we'll consider the possibility that maybe order of G is some particular finite number n. Let's first look at the case, though, where the order of G is infinity, and see what happens then. If the order of G is infinity, then we can actually apply a problem from the homework. I love it when this happens, because it makes me feel like there's some method to the madness. So in this case, the particular problem to look back at is homework 4, problem 2a, which says that if G has order infinity, then whenever G to the I equals G to the j for some powers I and j, it follows that those two powers have to be equal. And if you think about the contrapositive of that statement, it says that if you take G and you raise it to two different powers, you'll get two different answers. So in other words, if I look at this list G, G squared, G cubed, G to the 4th, and so on, those are all different elements. No two of them are the same as any other. But those are all elements in our group capital G. So we've found infinitely many elements in the group capital G, meaning the number of elements in G must be infinite, which is equal to the order of the element lowercase g. And so that proves the statement in this case, in the case where the order of G is infinity. How about the case, though, where the order of G isn't infinity, but instead is just some particular finite number, like 4 or 5? So let's give a name to that order in this case. Let's say the order of G is some particular number n, and then let's start writing out the elements of the subgroup generated by G. It would have the identity and G squared and so on. At some point I'd get to G to the n-1 power, and then I'd want to write G to the nth power next, but if n is the order of G, then that means G to the nth power is equal to the identity, which I've already written down. And then from there, it also means that G to the n plus 1st power is the same as G, which I've also written down. By the way, one thing I encourage you to convince yourself of is that it also means that G inverse is the same as G to the n-1 power. If you're not convinced of that, try multiplying G to the n-1 power by G and making sure you get the identity. So the punchline here is that I can keep raising G to more and more powers, or raising its inverse to more and more powers, But I'll never see anything besides what I've already written down, which is the identity, g squared, and so on, up to g to the n minus 1. And if you count how many elements I've written down here, you'll see that I've written down n elements, so that's the number of elements in the group capital G, and that, by definition, is the same as the order of the element lowercase g, so we've proved our equation in this case, and that covers all the possible cases, because either the order of g is infinity or it's some finite number, and so with that, the proof of this theorem is done. So let me now remind you that what I advertised in the last video is that we have sort of an overarching goal for this week of the class, and the theorem that we just got finished proving is a step towards that goal. So the big goal, remember, is to have any cyclic group, capital G, it's generated by some particular element, lowercase g, and I want to give you a formula for the order of any element in that group. And all the elements are powers of this one element, lowercase g. So what that formula is going to look like is something that says the order of g to the k equals blah. So I claim, although I suspect it's probably still mysterious why this is the case, that the theorem we just got done proving is a step towards that goal. And now what I'll show you is the next step in that direction. I'll state this as a lemma, which is mathematicians speak for kind of a mini theorem, which is a step towards some ultimate goal. Here's what the lemma says. It says, let capital G again be a cyclic group generated by this element lowercase g, and let's suppose that this cyclic group has n elements. By the theorem we just got done proving, another way to say that is that we're assuming that the order of this generator lowercase g is equal to n. Then the statement is that if I were to look inside of this group at the subgroup generated by g to the kth power, or if I were to look inside here at the subgroup generated by g raised to the GCD of n and k power, then those two subgroups would be the same. So again, I suspect it's probably kind of mysterious how this lemma is a step towards our big goal of calculating orders. If so, don't worry, we'll tie all these loose ends together next video. But for now, let's look at least one example to try to make this lemma seem a little more concrete and hopefully kind of more believable. So let's suppose our cyclic group capital G, generated by lowercase g, has 6 elements. So in other words, let's suppose that lowercase g has order 6. Then we can write out what the elements in capital G are. They're exactly the elements of the subgroup generated by G, so they're the powers of G, which are the identity g squared, g cubed, g to the 4th, and g to the 5th. And I'll stop there because if I were to look at g to the 6th, that would be back to the identity. Now let's pick one of these elements, and we can pick whichever one we want. We're going to look at the subgroup that it generates. So for instance, let's say I pick this one, g to the 4th. So what's in the subgroup generated by g to the 4th? So it's got the identity, it's got g to the 4th, it's got g to the 4th squared, which you might say is g to the 8th. But if you keep in mind that g to the 6th power is the identity, then g to the 8th power is actually the same thing as g squared. And then what else is in this subgroup? Next might be g to the 12th power, but again keeping in mind that g to the 6th is the identity, then g to the 12th power is actually also the identity, because it's g to the 6th squared. And from there you could keep raising g to the 4th to more and more powers, but you're not going to get anything new. So the only elements we're really going to find in this subgroup are the identity, g to the 4th, and g squared. Notice here this is the same thing that we would have gotten if we had taken the subgroup generated by g squared. And that power of 2 there is exactly the GCD of 6 and 4. So if you flip back to the statement of the lemma on the previous slide, you'll see that what we've found here is exactly the statement of that lemma in the case where n, which is the order, is equal to 6, and k, which is the power of g we're studying, is equal to 4. So that's the idea of this lemma. In our next video, we'll prove the lemma, and we'll finally use it to prove our long-awaited formula for the order of an element in a cyclic group. So in the meantime, I'll see you in class.